like transport. Oh, okay. You can make, it's been interesting to many people as transparent electrodes, capacitors, solar cells, lots of different types of devices. Now, in my lab, we study mostly electronic devices, so we really care about graphene's electronic properties. In this case, electronic properties are given by the energy of two carriers, by two surfaces above each other. And you can see that these surfaces touch each other at these zero energy points. Because we live in a low energy world most of the time, we really care about transport around these zero energy Dirac points here. And so if you look at the energy here, you see that you basically get linear dispersion around the Dirac points, which defines the properties of graphene. And practically, that means when you're measuring conductivity versus gate voltage, you see that you have a semi-metal with a gate tunable conductance. And this is kind of rare for materials, because generally you have materials that are tunable, that are gate tunable but don't have high mobility, or that are not gate tunable like a metal, but that do have high mobility. And graphene sort of bridges this area, which makes it a great electronic material. On top of that, this Dirac point here, this is these low energy points. But because the Dirac point depends crucially on the band structure of graphene and on the doping, it can shift with strain and doping. And so even just a simple graphene sheet that you strain or that you add molecules to can act as an electromechanical or a chemical sensor, which makes it interesting for these sort of applications. Okay, so the question that we ask is, how do the electronic properties of graphene change when it's strained? Okay, and it turns out that there's a lot of interesting behavior that's induced by strain engineering graphene. This is an old paper, but it covers a lot of the behavior that's expected. So applying mechanical strain to graphene introduces energy gaps, can induce large quasi-magnetic fields, and generally enables different sorts of new flexible devices. There's a lot of interest in straining it and seeing the physics that appears. And it's just as one example, this is some years ago, but I think it's still one of the more interesting effects. This is a scanning tunneling microscopy experiment on graphene that was on a ostensibly flat surface, but they found that it was on, I think, platinum, and the platinum had little tiny bubbles in the surface, about a couple nanometers. And when they did scanning tunneling microscopy into the graphene that was on top of the bubbles, they found that the electrons were orbiting around these strained regions. And basically they could see Landau levels, cyclotron motion of the electrons and Landau levels that formed of the electrons in this highly strained region, where the Landau levels were consistent with a magnetic field around 300 Tesla. Now, we know that there's no external magnetic field here. This is just a little nanobubble of strained graphene where there's evidence of local Landau levels equivalent to what you'd see in a 300 Tesla magnetic field. And of course, as most experimentalists know, we can't access fields like this in the lab. I mean, any actual magnet at this size would, it would become unstable. The wires would also vibrate until basically the whole thing just blew up after much less than a second. So the fact that you can see the effects of 300 Tesla in this case shows you how interesting it is to strain these materials and get these really new behaviors. Okay, and why does this appear? This appears because of inhomogeneous strain. So it turns out that this little nanobubble, because it's kind of pyramidal shaped and you're stretching the graphene inhomogeneously around different directions, this inhomogeneous strain acts like a curling magnetic vector potential. So if you have this inhomogeneous strain field, it acts like this magnetic vector potential A, which curls. If you can see this here. Oops. Is that okay? That's fine. Okay, is this showing up on my screen, or is it okay?
Yes, we have a question from Alex.
Yeah.
Yes, please go ahead.
So I always get confused about this. I should remember the answer, but I never can.
Yeah.
Magnetic field breaks time reversal.
Yeah.
So if I pass the current one way, the Hall deflection is to the left, and if I pass it the other way, the Hall deflection goes the other way.
Yes.
Strain doesn't break time reversal.
No.
So it's sort of a pseudo-magnetic field, right? But it's not a real.
Yes.
It's not a real magnetic field. It's more of a a guiding center, like ions are guided through a bent crystal?
I think that's correct. I mean, so this pseudo-magnetic field does nothing to spin, for example. It doesn't break any spin symmetries or something like that, right? So I think of it.
But it also doesn't cause a Lorentz.
It doesn't cause a Lorentz. It doesn't cause a Lorentz force. No, it doesn't. That's right. It doesn't cause. That's right. It doesn't cause Lorentz force and it doesn't break spin, but it doesn't do cyclotron motion. I think of it almost like I think of local. I mean, so basically what you're doing, if you're straining graphene in a certain way, you're inducing phases, right? In this case, represented by the vector potential that allow the electrons to basically orbit in a circle, right? The way the phases accumulate gives it a higher probability of just orbiting in place. So I think that's how I think of it, at least, right? Does that make sense?
Yeah, so it couples to A, but it doesn't cause a Lorentz force. Is that it?
Yes. Yeah. I mean, okay. So what I've shown here is it creates a gauge field, right? Which basically goes in as an e to the I A H over E term, right?
Yeah.
Where A is just this term due to the strain.
And it has opposite signs in two valleys. That is why electrons from two valleys, they rotate in opposite directions.
Right.
May I ask a question?
Okay, thanks.
Yeah.
It's strange. There must be Lorentz force, of course. If trajectory is curved, there is a Lorentz force. That's no doubt.
Oh, you mean, okay, sorry. So what you're saying, right. So there's an effective Lorentz force in that they're moving in a circle, right? So something has to be moving them in a circle. It's just that.
Yes, of course. Yeah,
yeah. I mean, I guess, okay. All I'm saying is that it's not, you're not going to get linear behavior out of this, right? You're not going to get a magnetic field that causes an electron to move in a straight line the way you would with the true Lorentz force. Is that? It's only going to be orbital from this sort of strain.
But if you valley polarized it or created a valley imbalance, then you would pick up a Hall voltage. Because the two valleys have opposite. It's because the two valleys have opposite effective. You could think of it almost as charge.
Mm-hmm, mm-hmm.
So, yeah, okay. I think we'll use. All right.
And
Yes.
I also have a question. How small is the magnetic length? So how many orbits is per such, I don't know, dot, so, or this strained region?
I mean, I don't, in this experiment, this whole structure is 2 nanometers.
So
And
the magnetic
so,
length would be about 3 nanometers.
Yeah.
At
Yeah,
300
and you
Tesla.
can, yeah, and you can see how the field. I mean, you can see how the pseudo field is plotted in red here, and it's pretty constant over this scale of about 3 nanometers. But I believe it falls off after you get to the edges out here.
Okay, thank you.
So a few nanometers, I guess. Yeah. Yeah. The question about valley polarization is interesting. I mean, this is the sort of thing that we're trying to do now. We're trying to look at different sorts of Hall effects and under different conditions. I haven't seen a lot of predictions about it, honestly, but maybe they're out there. I'd love to see references if someone had those. But yeah.
Thank you.
Sure. Right. So yeah. So and then one of the points here is that it's a this only happens for non-uniform strain. If you had a uniform strain field, you wouldn't expect to see this pseudo-magnetic field. You could see other effects, but not the pseudo field in the same way. Okay, so experimentally, our goal was to, this had been seen via STM, but our goal was to see it in a device because, well, if you want to make something practical, you want to see it in a device. And also interesting things can happen along edges and other areas on the device scale. So to see these sort of pseudomagnetic field effects or any sort of strain effects like this on the device scale, we really had to induce some sort of global pseudomagnetic fields, not just local. And we also had to be able to fine tune the strain to the graphene to make sure that we had some type of non-uniform strain that extended across the device. Now, you can think of different ways of just pulling the graphene. Pulling it laterally wouldn't work, but if we could apply a triaxial strain, that would be great. And there's some interest in doing this. It's just it's not that easy to do this on an actual device on a substrate. You can have piezo's in multiple directions, but it was a little harder than what we wanted to start with. So what we realized is that if we had periodic pseudofields, that we could possibly realize this. And so we ended up thinking about ways of making periodic features on our substrates, and then using that to get periodic strain across the device and getting an average pseudofield or average behaviors there. One thing I want to note is that the length scale here matters. You want periodicities in the scale of between 10 and 100 nanometers. For periodicities of these features that's below 10 nanometers, you start merging with the Dirac point and it becomes really hard to see features. For things above 100 nanometers, you have to apply such a big gate voltage that it's really hard to see. So we really wanted to ultimately make features that are around the 10 to 100 nanometer scale in order to see these sort of effects. Okay, so when we first started this, there weren't a lot of techniques to controllably and globally control strain in these sort of 2D materials. I'm mentioning this, I mention this often for students because when we first did it, I just put an undergraduate on it and we did the most ridiculous thing you could, the easiest thing you could imagine, which is we just took a polymer and he made this little stretching device that to me looks like one of these medieval torture devices where you just clamp it down. And then we hand wrote grids, transferred graphene on top, and then just pulled it apart. Okay, and then looked at it under an AFM and also put electrodes on it and measured what happened as we stretched it. Now, what happened was what you might expect to happen because it's on a rubbery substance. It basically just kind of cracked and pulled apart when we pulled it. But it turned out even that was a little bit interesting because if you look at these images, this is the first one is with no strain, and then we apply some strain and we open up this crack. But then when we reduce the strain again, it looks like the crack almost completely closes. And then when you measure the resistance, you can see the resistance increases when it's cracked and then goes back again, and then increases and goes back. And basically the resistance goes back almost to where it was. And so, this wasn't what we wanted exactly, but it did show something interesting. One was that even when you form cracks in graphene, they don't keep opening uncontrollably. It's not like opening a piece of nylon where the rip just keeps extending after you've done it. It's self-limiting, and not only is it self-limiting, but when you close the crack, because graphene is flat, you get enough of an overlap region that the resistance goes back almost to where it was. Okay, so this was just a kind of practically interesting result that gave some hope for that. Even if you have graphene mechanical devices and they do crack, you can still use it for things and have behaviors that you expect. It's pretty resilient. Okay, but that was making lemonade out of lemons because we really wanted to avoid cracks in this case. So after this, we moved on to these micro patterned substrates. And again, I started.
Could I interrupt you?
Yeah.
Does the presence of cracks assume that electrons couldn't hop across it? It is just.
Yeah. These are okay, and I keep thinking I don't have I should have a length scale on these. I'm sorry, I don't. I think that about half of this is about, let's see, these cracks are maybe 500 nanometers or something in width. So they're pretty big. So this crack here is maybe 500 nanometers. So they're big. I mean, is that what you're asking? They're bigger than you'd expect to hop across.
Okay, I see. Yeah.
And besides that, because the cracks were sort of self-limiting, they tended not to extend across the whole device. We'd get just regions of cracks. And so the conductance was always going to be much larger going around them than even tunneling through small regions of these. That makes sense. Yeah. So I think that's what was dominating it. Okay, so then we moved on to these micro pattern substrates. Again, we started with an undergraduate project because I just wanted to see if it worked. I was sort of stuck on these pyramids for a while, and the best way I could think of as making pyramids was taking just a plastic mold and nano indenting it. The nano indenter has a tip that's a couple microns in diameter, but you could easily nano indent into plastic, and then we poured PDMS over this and cast it, pulled it out, and then typically put a metal or oxide on top to make it rigid, and ended up with features that looked like this. Now, the nice thing about them is they're beautiful pyramids, and we could also control the spacing of these. to see how the effective spacing had on the overall strain in the graphene. So we then transferred graphene onto these controlled arrangements of features. Here's, you can see graphene on top of the pyramids. Here's the pyramids without graphene. And what we found is that the graphene pinned to the top of these and was strained at the apex of these features. So how do we know that? Well, we looked at just atomic force microscopy of them. And you could see the AFM images of graphene on top of different spacings of pyramids. So here's 4 micron spacing, 3 micron spacing, and 2 micron spacing, the closest ones. And if you look at the 4 micron spacing, you see almost nothing. It's just the pyramid tips. And that's because the graphene just conforms really well to the pyramids and the space between them. So it's just draped over them and conforming. But as you make the spacing smaller, you start to see other features, these wrinkle patterns form. That's because the graphene is getting strained and starting to wrinkle between the pyramids, until at the 2 micron spacing, the graphene lifts up off the substrate altogether because there's a competition between the adhesion at the bottom and the strain it feels at the top of the pyramids. So basically by de-adhering, it shows that it has much more strain when it's only spaced by 2 microns. So this is interesting to us because it showed that we could control the strain in the graphene by the pyramid spacing, meaning that it really was pinned and strained at top of these pyramids, and that we could get this controllable strain over a large area just by having the graphene pinned to these features. Okay, but at the same time, this nano indentation technique was pretty painful, very slow, and PDMS wasn't compatible with electronic devices that we wanted to measure, as well as smaller features. And so after seeing that this worked, we moved on to nano-fabricated pillars, which seemed to make a lot more sense in terms of measuring transport in these devices. So in this case, we started with silicon oxide substrate, put copper caps on it, used the copper to etch out nanoscale pillars, removed the copper with copper etch, used a BOE etch to make it sharper, put down contacts, transferred our graphene from solution, like I mentioned before, etched the graphene, and then we had our devices. Easier said than done, but here's some SEM images of the actual pillars. Here's the sharpened devices, and you can see in this little inset that the tip of these sharpened devices is about 20 nanometers. Here's graphene that was transferred on top of the pillars. It didn't generally rip. I'm showing you a region with a hole so you can see the contrast between the substrate, which is dark, and the graphene on top of the pillars here. And then the whole thing was patterned in a way that we could make electrical contact to it in 4-point measurements. Okay. And this was nice for us because we have now nanoscale pyramids with sharper features, and it's suitable for transport measurements overall. Okay, so now we can measure transport in these, but because we're no longer looking at adhesion and de-adhesion, we really want to be able to tell that it's strained, because none of this, even though we know the graphene's pinned, none of this is valuable to us unless we also know that it's strained. So in order to measure the strain, we end up using Raman spectroscopy. Okay, so Raman, of course, measures these vibrational modes of graphene. And this nice paper that came out some years ago showed that you could actually differentiate between strain effects in graphene and doping effects in graphene by looking at the ratio of the shift of the 2D peak to the G peak. So the 2D peak is related to the disorder, and the G peak is, I think, this one here, one of the vibrational modes. So all of these, you can shift these Raman peaks by strain or by doping. But if you shift the Raman peaks by strain, then the ratio of the shift of the 2D to the G is a factor of 2. If you shift the Raman peaks by doping, the ratio of the shift of the 2D to the G is 3/4. So you just have to look at how much each of these peaks shift and then plot their ratio to see whether you're strained or doping or some combination of the two. Okay. So then this is exactly what we did. We took our graphene on top of the pillars, like here, okay? And we took the Raman spectroscopy, and then we compared it to the spectroscopy of flat graphene. Okay, so the blue is flat and the red is for the graphene on our pillars. And what you can see is the ratio of the shift here is we're shifting along a line, a slope that's almost parallel to what you'd expect for strain, a factor of 2. Okay, so if by putting the graphene on the pillars, we were mostly changing the doping, you'd expect it to shift along this line. But by seeing it shift along this line here, we could show that we're really mostly straining the graphene on average by putting it on top of these pillars. And you can extract the average strain of about 0.1%. Now, these pillars are separated by like 700 nanometers, so they're pretty well separated. So even getting a 0.1% strain on average is nice because we're getting device scale strain, whereas we think that at the apex of these pillars, the strain is actually greater than 1%. So very strong strain at the apex, but an average strain nonetheless across the entire device. And now we can measure transport and see what happens in this case. So these are 2D plots of resistance as a function of gate voltage and magnetic field for the graphene on pillars and the flat graphene. And in this case, the red is high resistance and the blue is low resistance. And so what you see for the graphene on the pillars is we get these regions of high resistance around zero field as a function of gate voltage, these confinement regions. Whereas in the flat graphene, we see nothing in this same region. Okay, over here we have the beginning of Landau levels, right? Because we're looking at a strong magnetic field. So we're ignoring this for now, but in this region of interest, we don't see any confinement for the flat device. Okay, so why do we have confinement for the graphene on these pillars? Well, the one thing you could say is, well, we just have charge variation. Maybe it's just charging effects because we have a lot of spacing between our pillars. And so, you know, the graphene that's confined up here is in these little, regions of about 40 nanometers of connected to the pillar. And then in between we have something else. So maybe we have confinement just in these small regions. And in fact, you know, if we think about these delamination regions, we expect some sort of suppressed scattering in here for small dots. And in this case, if the dots are smaller than the typical cyclotron radius, then we expect to have suppressed scattering and suppressed conductance. And so this is at least consistent. This is consistent with what we see, that it could just be confinement due to these delamination regions and the crossover between suppressed forward scattering and the cyclotron radius. Okay. But it could also be an effect of a possible pseudo-magnetic field, because if you simulate the strain at the top of the pyramids, you can see that you expect to see a pretty large pseudo-field. You know, I have to say, this is a paper where we were being very conservative. When we first submitted this, we tried to be really conservative, and we thought it might be a pseudo-field, but we couldn't really prove that it was a pseudo-field. So we only wrote in that it was a delamination region. And the referee wrote back saying, how could you not say it's a pseudo-field? You have to assume that it's also a pseudo-field. So it's true. We can't tell in this case. Yeah, Dimitri.
Am I correct that could you show this dependence of resistivity or the conductance again? Am I right that it can be seen as a Shubnikov-Dehas oscillations of conductivity as function of gate voltage when the chemical potential cross Landau levels, or not?
The oscillations you see for Shubnikov-Dehas are generally as a function of magnetic field.
Okay.
Right. So that would be on the vertical axis.
Oh,
here.
I see.
So the horizontal axis is gate voltage, whereas the vertical axis is field. So there is confinement here as a function of field, but you know, I would say it's at some average scale rather that it doesn't look oscillatory in the same way to me. Right.
Dimitri, it's difficult to. So if you were at a fixed field, Nadia, then the gate voltage, then you would get oscillations, right? So if you were at a fixed pseudo-magnetic
irregular, but yeah.
But the thing is, at zero magnetic field, as Nadia's saying, Coulomb blockade oscillations are also periodic in gate voltage. You can get lots of things that are periodic in gate voltage. And the density is potentially fluctuating. So it would be a very brave person to make that claim, right?
I see. I'll
show you more. I'm building up. I'll show you data where we're really certain we have pseudo field effects.
Okay, thank you.
But this was interesting to us because it is, you know, you can't tell. And this is sort of a lesson that you don't. There are multiple effects that can come in. And I mean, now looking back, I'm pretty sure we do have pseudo field effects in here. It's just really hard to isolate them. And as we know, especially with mesoscopic physics, the key is in isolating the various mesoscopic effects that can happen here. So I'm personally sure we do have pseudo field effects. It's just really hard to tell in transport in these experiments. In STM, you could for sure if they were clean. Is that?
Thank you.
Yeah. Yeah. So you know, but you can simulate these field effects, and you can say that you should have a very strong pseudo field. And in fact, you know, people have done similar experiments on holes like this. and made assumptions that they are in fact seeing these, that they are getting confinement from these high intensity pseudo-magnetic fields, even from these holes, which is something comparable to what we've seen. So, it's very likely, but it was really hard to tell in these particular experiments. And so now I'm going to tell you our last and most successful attempts at straining graphene on this level, and where we could really see all these effects without having to average out the effects of doping or of other behaviors, that Coulomb charging and things like that. And we were able to achieve this by, instead of looking at fabricated pillars, making the material do the work for us and spinning nanoparticles onto a surface and then transferring graphene on top of this. Now, in this picture, it looks like, okay, this isn't great curvature. How can you do this? But actually, these nanoparticles were about 10 to 20 nanometers in diameter. They varied between 10 and 100 nanometers. And so each of these nanoparticles is basically the same diameter as that very sharp tip at the top of the pillars, right? So they're really, really nanoscale, and you're getting a really large amount of curvature of the graphene as it sticks to these things. It's just that because we spin these nanospheres from solution, we can get these close packed arrays. And so we spin these on, we get these puddles, and this is a little hard to see, but you can kind of see the crystallization in here. There's a several micron wide puddle of nanospheres, and we find these regions on our substrate and then align the graphene on top. Okay, so we get these quasi-crystalline regions of close packed hexagonal, close hexagonal packed nanospheres that then allow it, that the graphene will then also pin on and strain, but now uniformly relatively across the device. And this is an MD simulation of what the graphene actually looks like as it's on top of the nanospheres. And in fact, we worked with collaborators who did transmission electron microscopy. It was not easy to do this on these devices, but this is a cross section where you can see the spheres. And then you can just barely see the graphene here, but you can see clearly that the graphene is pinned at the apex of these spheres and then is relaxed in between. So the graphene does pin at the apex, as we might expect, even on the nanoscale now. But the nice thing about these spheres is that, they're close packed on this scale of 10 to 100 nanometers, which was our target scale for seeing Fermi, changes in the superlattice type structure. It's relatively simple to get these large strain pockets, and as I mentioned, they're a pretty large, a small radius of curvature can give us large strain gradients. Okay, so what do these nanospheres look like? As I mentioned, they're close packed over several microns, close packed, pretty independent of size. This is a close packed array. This is just nanospheres, 20 nanometer nanospheres, 50 nanometer, 100 nanometers, 200 nanometers. And you can see that you get some grain boundaries between the crystal boundaries between these, but overall on the scale of microns, you get pretty nice polycrystalline behavior independent of the size. And then now we put graphene on top of these. And this is an atomic force microscope image, and here's what we get of graphene on top of these same nanospheres. So what you notice is that for the 20 nanometer spheres, you can see some features, but it's generally just sort of random, it looks like. And that's because there's it's basically conforming with some wiggles on top of the 20 nanometer spheres. This is like what we saw before, the pyramids closely and widely spaced. For the 50 nanometer spheres, you start seeing these herringbone patterns. These are wrinkles between the nanospheres. Okay, so these wrinkles are starting to form because the graphene it has space, there's space enough that you can get wrinkles in between. And then 100 nanometer nanospheres, you start getting more connected wrinkles until the 200 nanometer nanospheres, you get this nice network of wrinkles for the graphene that's on top of the spheres. Okay. I think there's something actually really interesting in studying the wrinkles alone and seeing how the graphene relieves stress. We didn't do that study partly because we're still thinking about it a little bit. But the one thing that this tells you is that there must be different strain then for the graphene on top of the different nanospheres if it's able to relieve stress in different ways. Okay, and so to measure this, we just have to turn to Raman spectroscopy again. And indeed, when we do this, we see very clearly that as you go from flat graphene to graphene on 200 nanometer nanospheres to graphene on 100 nanometer, 50 nanometer, and finally on 20 nanometer nanospheres, you're clearly moving almost exactly parallel to what you'd expect for the strain line. And again, this is really nice for us because these are pretty highly processed devices where we're spinning things from solution and we're putting things on. And you can see that you get a little bit more spread along the doping line, because obviously we're adding some random array of charges to the graphene. But on average, as you go between different nanosphere sizes, you're clearly mostly straining the graphene on average across the device. Okay. And you can plot this. Oh, sorry, go ahead.
Alex, please go ahead.
This is so cool. Just quick question: how uniform is this over this artificial lattice that you're creating with these nanospheres? Presumably, it can form domains, right? When the nanospheres come down and kind of self-aggregate into do you have a feel for how uniform this artificial lattice is, over what length scale you end up with domains?
Yeah, I mean, you can see it kind of from here. So let's look at this one, the 50 nanometer nanospheres, or I don't know, the 200 nanometer, right? You can kind of see that it's crystalline within this whole region here.
Right.
And then there's a domain boundary there.
Yeah.
And then it's crystalline there again. It's a little harder to see for the smallest ones because they're a little bit more irregular, but what we find is in general, if you look at these length scales, you get something that's polycrystalline on about the 250 to micron length scale. Okay. And so we make, as I'll show, we make our devices typically about 1 to 3 microns. And so we might have 4 or 5 domains in there. And so you can actually, I'll show you can actually see Fourier transform peaks on these, which means that it's still structured enough that you're getting the effects of crystallinity, but not perfectly.
I have also a question. What bounds the nanosphere size? Can they be made even smaller?
Yeah. So these are commercially purchased, which is another nice thing for us. These are just silicon oxide nanospheres. They're commercially purchased. The thing, so they do go down to 10 nanometers. They get a little bit harder. They clump together more as you get smaller. The other thing that you notice is that if you look at the 200 nanometer spheres, they're pretty regularly shaped. Whereas if you look closely at these 20 nanometer spheres, they're a little more irregular. So we ended up working with these 20 nanometer nanospheres because the 10 nanometer ones were just too irregular. They started clumping and became more and more irregular. So commercially, you can get down to 10 nanometers. We do work with a chemist now who can make them down to 5 nanometers, but they're still a little harder to get into nice arrays at that length scale. But there's no intrinsic. People make these sort of structures all the time at 5 nanometers or so, I think. Yeah.
Okay, thank you.
Yeah. Okay. Right. So what we showed is that these smaller spheres had larger average strain, and in fact, you could see this the average strain is going up to 0.3% on here. And again, this is just average over when we do Raman spectroscopy. The Raman the beam is micron sized or something, right? So we're averaging over the device, and yet we're still seeing an average strain, which is really nice. So it's big enough that even though you're spacing out, you can still see it. And we expect again that on at the apex of these spheres, we're getting a much larger average strain. I should say, this smaller spheres leading to larger strain is something that's consistent with our theory collaborators who did molecular dynamic simulations. And actually, it turns out that if you just think about how materials can form to spheres, you might expect it to have uniform strain over any spherical device. But in this case, it really just has to do with how much of the graphene is in contact with how much of the sphere when you see the average strain. So it's not that it's actually locally straining it more, but it's not that it's a greater magnitude of strain. It's just that more of the graphene is strained on the smaller spheres, and that's what leads you to a larger average strain, if that makes sense. Okay. So that was nice. It showed that we could really control this in this way. We have MD simulations. We could show that we had a strain distribution that looked like it was in this lattice, where you could get up to 2% strain locally in this lattice. But then as you follow the field, you think, okay, this is a lattice of strain. If we have these periodic strain variations, could we see effects of a strain superlattice in graphene? I mean, that's what this looks like, is a lattice on top of the graphene of strain. And what would that look like? Okay, so superlattice. This is a very hot topic all the time. I just came back from the March meeting, and there's lots and lots of sessions still on 2D materials and twistronics and super lattices. Super lattice is just any sort of long range pattern that modifies the band structure, right? So the pattern adds a secondary lattice. So here's one lattice, here's another material lattice, you put them on top of each other and you get a secondary lattice that has a structure that's typically larger than the lattice of either original material. Okay, and of course, this has been famous originally by graphene and boron nitride. And the transport signature of these sort of super lattices are secondary conductance dips. And so you can think of it as you have a Dirac point due to the original lattice, and then a Dirac point due to the super lattice itself, or a mini band dip in the conductance. That's basically what it ends up looking like. So what you see is, as a function of carrier density, you get your Dirac point, and then you get a secondary dip from just a fourfold filling of the superlattice at some commensurate point. And this is an experiment. This is for graphene on boron nitride. So this is the same thing that we would be looking for in our strained superlattice. Okay, but what energy scale would we expect to see that? Well, if we start with our structure, here the hexagons are the light colors are just our original graphene lattice structure. And then the dark areas are where our nanoparticles are. Okay, so if we're looking for a superlattice effect, we'd expect to have a unit cell that's just our nanoparticle size, which is about 21 nanometers, if you give a little bit of space between the nanoparticles. And you expect to see these secondary Dirac points show up and when you have a fourfold filling of these lattices defined, of the unit cell defined by our nanoparticle. Okay, and so you can calculate very, very simply where that would be. Just take the area associated with this unit cell defined by the nanoparticle, assume that you have 4 electrons that fill it, and you expect to see conductance dips at a density of 1 × 10⁻². So if we fill 4 electrons per supercell, we should see superlattice Dirac points at 10⁻12 per centimeter squared. Okay, so now that we know what we're looking for, we just do that experiment. Okay, so we have a device that looks like this. We put leads at either end. This is an actual optical image of the device. Here's gold leads, and here's just a patterned nanospheres. You can see the scale here. It's about a micron across. And relevant to your question before, it's a polycrystalline lattice. We expect a couple domains across, but you can still see pretty decent peaks in the Fourier transform of this sort of device. So it shows that it is really, the crystallinity is okay. Okay, so now we measure transport across this thing, and we see something that looks like this. This is the flat graph. This is conductivity as a function of density or gate voltage. And the black is flat graphene. And then the green, the red, and the pink, purple, I don't know what that is. It's called purple. The green, the red, and the purple are graphene on nanospheres. And if you look closely at this, you can see already that there's a difference, that you're getting, it's pretty linear out here, and then you're getting a change in slope around 10⁻². Now, this is a little bit hard to see because these have been processed differently. But if we just say, okay, at very high densities, let's assume that they all basically act, let's normalize the behavior to the high density behavior. So if we normalize this and say, we're normalizing the high gate voltage region, okay, and then seeing what happens as we go down to lower gate voltages. For the flat graphene, it's still very, very straight, as you might expect. Okay, we've just linearized it, normalized the conductivity. But for the graphene on nanospheres, you can see that you get these very strong deviations that all happen at 10⁻². Okay, so we've not done anything except just normalized each of them, and you can see that they all are the same out here, and then you get these features, these deviations that appear at 10⁻². Of course, 10⁻² is where we'd expect to see superlattice Dirac points, and these kinks always occur at 10⁻². And so this is consistent with having a superlattice due to strain in these nanosphere devices. And just to mention, this is our data compared to what you see for graphene on boron nitride, and it's not perfect because we do have a pretty disordered system, but it's still pretty clearly there. And I should mention that this is the nice thing about these nanosphere systems is that unlike the graphene on boron nitride, which is mostly potential modulation, or at least a mixture of potential and strain, here it really is strain. And I'll show you why we believe it's a pure strain modulation. We have a wide range of tunability of periodicity if we have different underlying nanoparticles. It's not atomically precise, which is why it's not perfect, but we can use any material to get this sort of superlattice. We can use any nanoparticle or any 2D material just to get this sort of behavior. Okay, so what makes us think now that we really have the strange superlattice we expect? We worked with our theory collaborator, Matthew Gilbert, who did simulations on these sort of devices and could show, for example, that if you have a perfect lattice, you'd expect really strong superlattice dips like you see in the boron nitride. But then when they added disorder, and they added disorder, which was identical to what we see in our devices, right? So this amount of disorder is identical to what we see, and you could see again that you get these kind of broadened dips, more consistent with what we see, but you still get dips. And so even with this amount of disorder, it's consistent with theory to get these features at the secondary Dirac points. We also worked with them to make sure that there weren't charging effects. And I should say, one of the first things we did experimentally is we measured nanospheres on top of graphene. Because if we had charging effects, then you'd expect to see a potential due to the charging of the nanospheres on top of the graphene, and we should see the same behavior. But we didn't see anything in that case. We didn't see any secondary dips or any interesting behavior. So that was at least some experimental evidence that you really need the graphene on top of the nanospheres to be pinned, and it's not just the influence of the nanosphere potential itself. Okay, but we also looked at theory of what you might expect for impurities on the nanospheres, and our collaborators again could show that the difference in potential between the nanospheres and the substrate, for example, would lead to charge fluctuations and some residual carrier density, but that there is no systematic difference between flat and templated graphene. Okay, so again, this is consistent with the behavior we see being due to strain only. And finally, we took a device and thermally cycled it. And what we found is, this is the original strained device of graphene on nanospheres. When we thermally cycled it, it released some of the strain. It's just, because it's just pinned to the surface. When you thermally cycle it, it's just released a little bit of that strain. But when we measured that device the second time, the first time you got this very strong superlattice dip, and the second time it was weakened after the strain was weakened. And so again, if the charging effects would be identical, but the strain effects were weakened and we see a weakened superlattice dip. And so this again tells us that we're seeing these strained superlattices, which is really interesting. Now, I started out by talking about magnetic field behavior. So what does magnetic field behavior look like in these cases? So again, what we expect to see for graphene in a magnetic field is quantum Hall effect. So just basically for flat graphene, you'd see a fan diagram where basically you're occupying Landau levels, and these levels are filling with field and with density, and so they just disperse with field and density in this fan-like shape. And this has been seen in graphene with superlattices, that you see this dispersion and you see secondary Dirac points with their dispersion as well. Okay, and so when we measure our devices, if we first start with just flat graphene, we see pretty nice Landau fans. This is just due to just charge impurities around the Dirac point. So there's no real features here. It's just an excess of conductance. But basically, we see these nice Landau fans. But if we measure a very highly strained device, you can pretty clearly see a secondary Dirac point there. So here's a primary Dirac point, and a secondary Dirac point appears just in these nanosphere templated devices. Okay, so this is our largest strain device, we think, and we can clearly see the effect of the superlattice in magnetic field. But what's interesting that hadn't really been seen before is we take an intermediate strain device. What we see is that basically at low fields, we can see these secondary Dirac points are kind of weak. And then they evolve around 4 Tesla into what you'd expect as a standard flat graphene Landau fan diagram, Landau fan. And so what this seemed to imply to us is that whatever pseudo-field was creating these secondary Dirac points and was dominating only until 4 Tesla. And then after that, the external field took over. And so maybe our average pseudomagnetic field value was something around here. And so we worked with, again, our theory collaborators to model this, and they could simulate basically our data showing these secondary Dirac points that evolved into Landau fans. But in order to do this simulation, they had to assume an average pseudomagnetic field. Okay? And when they assumed an average pseudomagnetic field of around 5 Tesla, they could get simulations that looked like our data. And so this was, again, to us, this was really the first, device scale transport measurements, evidence of pseudomagnetic fields in these devices, and showing a competition between external and pseudofields in these sort of systems. And again, 5 Tesla might seem small compared to 200 Tesla, but this is on average across a device, which was really interesting to us. We also wanted to see locally what the pseudofields were. So we worked with our collaborator Vidya Madhavan, who does scanning tunneling microscopy. This was a very hard experiment because STM people don't like working on devices that have polymers and nanoparticles and all sorts of processing, but through some great feats, they managed to actually do STM. This is kind of messy because our samples were so dirty relative to what they're used to working with, but you can kind of see the nanospheres here. This is an STM topography image, and you can see a nanosphere here, a nanosphere here, a nanosphere there, okay? And so then when you do spectroscopy across these nanospheres, you get data that looks like this. This is tunneling conductance as a function of bias voltage, where what you see are basically evidence of both integer and fractional quantum Hall effects. And this is at 0 external field. Okay, so they could extract quantum Hall effects from that dispersed as root n, as you might expect, across these nanospheres from STM. And then if you extract the local pseudofield, again, 0 field measurements, but if you extract the local pseudofield, you can see that it's around 55 Tesla, with the maximum at the edges of the nanospheres. Okay. So this is preliminary data. we're retaking this, but to us, it was really nice evidence that we see what we expect and more. And I should mention that there's this really nice paper out of Eva Andre's group at Rutgers showing evidence of flat bands and correlated states. In this case, they had, again, just these little bubbles that happened to be on a substrate. They're 0.5 nanometer, and they saw these pseudo gaps in these partially filled bands that they believe was evidence of correlations in their system. And we see nearly identical things here. So, in the between the spheres, we see these oscillations like what they see, and then on the peaks themselves, we see these split partially filled bands, which is very consistent with what they saw for these flat bands. So again, I don't want to. We're still analyzing this data. I just wanted to point out that what's been seen in what's been published before for flat bands on on non-engineered surfaces, we can see on our engineered surfaces, and are now trying to study more. Dimitri, did you have a question? I'm sorry.
Yes, we have a couple of questions. Aiden, please go ahead.
I was just wondering if we could create valley polarization by a simultaneous application of magnetic field and strain.
So I mean, that should be, I mean, this data does have simultaneous magnetic field and strain, right? This is an external magnetic field, and the graphene is strained. So what would you expect to see in that case?
I don't know the precise transport signature of it, but judging on the fact that strain causes bending of different valleys in different directions, and magnetic field kind of tilts the balance of this, I would expect a valley polarization if both strain and magnetic field are applied at the same time.
So we're applying a perpendicular magnetic field.
Okay.
Is that, do you mean perpendicular or in plane?
Perpendicular, yes.
Yeah. So the answer is Aiden,
I think
so I'll say one thing. Oh, sorry. I'll say one thing here, which is just that when we look at for this device here, when you see where the secondary lattice starts, it's still around 1 × 10⁻¹2, which is what you'd expect. I mean, at 0, okay, so maybe you would see it here. So at 0, you'd expect something at 10⁻12 for a 4-fold filling of our superlattice, right? If we were breaking the degeneracy, I think you'd expect to see that shift slowly as you add magnetic field. Is that correct?
Oh, okay, I'm not sure.
I'm not sure either. That's just a guess, because if you add field and you're breaking that symmetry, then you might have this shift over to something that's a factor of 2. It's not, I don't know if it's quite, I don't see it here, but I don't know if we have the resolution to see it here either. Would that be?
Okay, well, I'll take that as an input and think more about it, perhaps.
Yeah, I'm interested in that. Like, I would be very interested in seeing that also if that happened. I don't from the data we have, I haven't seen clear evidence of it, but it doesn't mean that it's not there because we are somewhat resolution limited just by, you know, the polycrystallinity and the samples themselves a little bit.
I think that Landau fan can be shifted. So the center of the fan will become a finite magnetic field when it compensates strain-induced magnetic field in one of two valleys.
Would that mean, would I see, I mean, so basically, I think that we did that. I mean, so you want to see where right. So where does the fan converge, right? And I believe that these converge at 0, as I recall, right? That's what you're saying, that the slope here would converge somewhere that's not 0 as you apply strain. And I think, as I recall, that these converge back to 0. I mean, I can make me want to take out my ruler and put it to the screen, but I think that I don't have anything on here, but I think here, I'm gonna do it right there. I think yeah, these basically converge back to 0. So I know that we looked at that at some point.
We also have a question from Abhaygapta. Sorry if I mispronounced.
It's okay. It was a nice talk. So the normalized conductance plots you showed for to see that there's a secondary Dirac point existing. So I was trying to compare the experimental plots with the theory plots you showed in the next couple of slides. So after -1 or +1 10^12 centimeter square, your normalized conductance for the strain and the flat graphene is similar.
Well, I mean, that's artificial. I mean, we made them that way. That's all. I mean, we pinned them here. That's all we did. So that's, I mean, it's not, you know, they start out, the raw data, it's not the same at all.
Yes.
So what we did in this process is we said, let's assume that for the highest gate voltages, they're all, let's scale all of these nanosphere plots so that they're the same as the flat graphene for high gate voltages. So we just scaled the values out here. Does that make sense? And so then when we did that, then we saw that they all scaled, you know, we artificially scaled the value here, and then it tracked until you got to this point.
Okay. So I was just confused. If I was just thinking if that means after the secondary Dirac point, they have the similar band structure, but between the primary and the secondary Dirac point,
no. This is an artificial scaling. The only reason we do this is because, you know, because the samples have other differences, right? At high gate voltages, they're different because they're on different substrates and they have different, you know, they have different densities just due to the way we process them. And so it's a little bit, you can, I think you can see in the raw data where these dips are. I mean, I definitely see dips here and I definitely see a dip there. It's just that because they're so different out here, it's hard to compare where they happen. So this was just an artificial pin the high gate voltage values to each other by just multiplying each of these by a factor, right? And then see what happens as we get to the low gate voltages. There's nothing else.
Okay.
Sorry,
Thank you.
I think we have also a question from Alex.
I just wanted to add in a comment to the previous discussion about Aidan's question about valley polarization and Dimitri's point. I think the Landau fans still have to go back to B = 0 because you haven't broken time reversal. I think it has to be symmetric around B = 0. But I think if you were to pump it with circularly polarized light, maybe, then you could preferentially populate one valley compared to the other. And then the plus B data and the minus B data presumably would be different. Because you're pushing stuff into the two valleys will feel different Lorentz forces essentially. So you're creating an impopular. If you think about in the extreme case, you know, if all the carriers are induced only by the circularly polarized light, then you would only be introducing into one valley. So you'd have then you would get a net offset. What we were talking about earlier of the effective magnetic field, but on average you don't get an offset because half of the you get +5 Tesla for the K valley and -5 Tesla for the K prime valley. So the net effect is sort of 0.
0, yeah. So
That's
we
sort of my,
you wouldn't see any effects of valley polar of breaking that degeneracy on transport necessarily, is your thought.
right. But if you could lift somehow, if you could lift the valley degeneracy, then
Well, it's funny because I always think of lifting valley degeneracy via strain, but in this case, the type of strain, the strain in this way is just, we're doing it quasi-symmetrically, even though it's non-uniform. So.
oh, but if you were to pull it,
Yeah.
that might be interesting. Then, like, to you go back to your medieval torture device and.
Right. So what we'd want is something that's both on a pyramid like this and then an additional strain in some direction. Yeah, which would be interesting. So you need both non-uniform strain that's has different magnitudes. That would be, and in fact, that's something that is something we're thinking about now. We're thinking of ways to do this sort of thing, but that's interesting.
Yeah, because then you could use the uniform strain to lift your K prime degeneracy and the non-uniform strain to give you over a larger length scale your artificial magnetic field. Maybe.
Yeah. No, I mean, I think I didn't mention, but I think all of this data was taken at low temperature. I mean, we don't to take these sort of Landau fan diagrams and things like this. I don't remember exactly, but I believe it was probably helium-3 temperatures. It was somewhere between 300 millikelvin and a Kelvin. So it's not optimal for putting in polarized light, at least in our systems. It can be done, but unfortunately,
the strain idea sounds much nicer because you can then separate the two things really nicely. Right. Anyway, sorry.
Right. No, it's interesting. And these days people are putting piezoelectrics and things in their systems. I think it would be a very interesting thing to do. Absolutely. I think, well, I think that was really my last physics slide. So,
I think you also have two questions.
More questions. Excellent. Yeah.
We have also a question from Fiaksang.
Yes. Thanks, Nadia. It's very nice talk. Yeah, I think it's amazing to use nanoparticles to create a pseudo-lattice with strain. I'm just wondering, how do you actually package them together? And is it possible to remove the boundaries? Because I saw you have some boundaries, so it's not like a single crystalline sort of pseudo-lattice. So you have basically have a polycrystalline pseudo-lattice. Then so then I'm wondering, how can you sort of remove boundaries so we can see a more clear transport signature?
Yeah. So we're working on that. I mean, right now we just spin them on and then look for these regions. So we're working with a chemist, Chan Chen, who's in she's in material science at Illinois, and she's making different sorts of nanoparticles. So the problem is that they can make perfect lattices that are long length scale by putting ligands and other things between the nanoparticles. Right. The problem there is, one, they're generally not single layer. When they do this, it's often sort of crystals of them, and we really want one single layer. We want it. The other is that adding, the more chemistry you do to it, the dirtier our graphene gets. And so when they started putting ligands between their nanoparticles, we started getting just really broad Dirac points. So we're still trying to figure out this balance between having, better crystallinity while maintaining a cleaner graphene interface to give us stronger, because the other thing is, if you can just get a higher quality Dirac point, you could also see all of this much more clearly. So, that means maybe putting boron nitride below it or above it. But then if you put it below, then it will reduce the strain a little bit too, because that'll be strained, but not the graphene on top. So I think it's a really, what you're saying is exactly what we want to do. It turns out it's not that easy with what we have right now. We could also make smaller devices, but as you get below 200 nanometers, you start, we really want to see average behavior, not behavior that's dominated by one particular set of nanoparticles or one particular edge effect or something. So there's a bunch of constraints. It's exactly what we want, but it's hard.
Yes. Okay. Yeah. Thanks. Yeah.
I think that's on my final slide of what do we want? We want cleaner systems. In fact, I think that's literally here. Improve periodicity. That's our number one goal. Improve periodicity and also improve cleanliness for STM.
Right. Yeah.
So
yeah.
Okay. Thank you. We have another question from Hayden. Please go ahead.
Hi, yeah, that was a really interesting talk. Thank you. So I was just wondering about this surface that you have underneath the graphene. So you were using, I think at the start, like pyramids and spheres. And I guess I was just wondering, how does the geometry of these underlying solids affect the strain and the electronic properties? And specifically, is there any way to kind of relate the geometry or the curvature of this flat graphene to the curvature of the underlying surface? Like,
so, I mean, so what, in what way do you mean, how does it affect it? Do you mean in terms of charging or just in terms of?
I guess I'm just thinking about if you had like, say instead of pyramids, you use something that was closer to like a cube. Does this like, how does this change of the strain affect this?
Yeah. In fact, it's funny you say that because our same nanoparticle collaborator has particles that are flat that look like cubes. And we thought about it for a while and then decided that it was just too complicated. So the thing is that, we started out with, we started out with the nanospheres because we were really trying to mimic this, the little nano bubbles that they've done STM on that gives you these sharp potentials that's non-uniform. Because we know that the sharp non-uniform pyramidal potential will give these pseudofields. My worry is that if you have a square, then what if the graphene pins at the top, but then you get, I mean, in theory, it could be the same, right? Because it pins in one area and then it's just non-uniform by pinning along the edges. We haven't done any modeling of what that strain would look like. I know what it looks like when it's kind of pinned at a round point, but a square point, I don't know if it's the same or not. I think it's interesting. It's just that, it's been hard enough to see the effects that we didn't want to change too many parameters. So, we're almost waiting for someone to tell us, hey, if you could do this on a flat particle, then you'd see these other cool things. Or if you could make something that's elongated and strained in one way and not the other, you could do it. The other thing is, we're limited because the graphene is just being pressed on. So the graphene sticks where it wants to stick. And we're not really controlling the area over which it sticks and the area over which it's being pinned. So, if we start trying to do funny business with elongated particles, we don't know if it's only sticking, if it's actually sticking uniformly, even if we make particles that are long in one direction, because it just depends on how it adheres and what the local strain is.
That's incredibly interesting. Yeah, I guess with the cube, if you had these kind of like underlying creases in the graphene structure, that'd be really interesting. But
I think it'd be really cool to look at. I mean, we might just try it just to see, but yeah, I think at the end of the day, they also clump together. Particles are really messy. I mean, this is why I didn't go into chemistry, because particles, they clump and they stick and they're messy. Yeah.
Yeah. Thanks a lot. I really enjoyed the talk.
Yeah, thanks.
I also have a question. Is it possible to extend this physics in 3 dimensions? I mean, if you make a layer of nanoparticles, then graphene is a layer of nanoparticles, graphene, and I don't know, at least a few layers.
Yeah, I think, I mean, so so again, the question is, what do we expect? What do we think we're going to see? Is it, would it be, these are 10 or 20 nanometers. It's not clear you're going to get interaction across in the lateral direction. So that's kind of big, right? And so then, do you think you'd see a larger strain effect on average? Because you're just going to be averaging over all these devices. So the answer is, I don't know. I don't know what you'd expect in that case. I don't know.
I know, multi-layer plasmonics, or the plasmons and multi-layers, they are how this called? Have hyperbolic behavior, and strain could affect it, something like this.
I mean, so you'd have to have communication across the 20 nanometers, which is a pretty big gap. But in theory, let's say you, I mean, I'm trying to think. Let's say you had graphene on nanospheres, and then like, I don't know. I don't know how you'd get another strain. Like, okay, well, and then boron nitride, and then graphene that's strained on top somehow, or graphene that's strained on the bottom and the top that's separated by a layer of something, and then you can actually get correlated behavior somehow across it. I think that could be interesting. I just don't know what you'd expect, right? especially that you wouldn't expect in just twisted graphene or something. I mean, that's the other thing, is that these aren't that, I mean, twists aren't that easy, but these aren't that easy either. And so we're trying to go after things that strain uniquely does. So, you know, strain uniquely creates pseudofields. You know, strain can uniquely create edge effects and things that you may not get just in a twisted system. So that's where we're going. What can you uniquely get with strain that you can't get with other electronic behavior just in a twisted bilayer or something like that?
Okay, I see. Thank you.
But I'm interested, I mean, I'd love to hear it, because I just don't know, but I want to, we are looking for ideas and things that you'd expect now. I never, here, I'm going to finish here's where I'm going. Okay, right. The last thing I want to mention, this is literally the last 2 slides, is that, you know, there are a lot of other materials, and this is the thing that, you know, this is kind of what you're mentioning. You know, you can make multi-layers of graphene. I'm not sure what you expect, but you can also do this on other 2D materials that could give you new interesting sorts of behavior. And, you know, this is an old paper looking at a solar funnel for moly-disulfide, but this is just, they applied an STM tip to the moly-disulfide. So imagine if you now had an array of strained moly-disulfide, you know, that it was controllably strained, could you get better behavior or device scale behavior by doing that sort of thing? And that's sort of what we're looking at now. And, you know, this field of straintronics and 2D materials is a really growing and exciting field. And, you know, we think that we have a unique angle for looking at a lot of these different sorts of behaviors. So there've been a lot of questions. I just want to end by thanking the people who actually did this work and my funding agencies at the NSF and the ARO, and then here's some references. So I will leave it at that if there's any more questions.
Okay, thank you, Nadia, for a fantastic talk.
Thank you.
Do you have any more questions? Please just go ahead. We had already made.
There were a lot of questions. Yeah, it's late and there are a lot, so it's okay.
Please just go ahead. And if not, let's thank the speaker again.
Okay, well, thanks very much. It was a pleasure. And the next time in person, I hope.
Yeah. So good luck to everyone and have a nice day.
Good. Thanks, Dimitri. Am I leaving now, I guess?